Hi, my name is Jonathan Poplawski, and I'm in charge of the Atom Probe Tomography Laboratory within the Center for Nanophase Material Sciences at Oak Ridge National Laboratory. And I'd like to thank you for joining me today in this webinar, where I'm going to show you some of the basics of atom probe tomography, including data analysis. I'm going to have a Q&A with Bert Vekhuizen from Utrecht University, in which we're going to discuss his experiences with the user facility, and I'm going to follow it up with a live Q&A in which I could answer some of the questions you have about the atom probe facilities. First, I'm going to show you some of the basics of atom probe tomography. The atom probe tomography facilities within the CNMS consist of two physical labs. The first lab is the sample preparation lab, which contains a Thermo Fisher Nova 200 dual beam scanning electron microscope and focused ion beam. This is where we can create site-selective liftouts from regions of interest of your choice, such as grain boundaries and interfaces within your sample. We then mount these liftouts onto a silicon microprocessed array and mill them into needle shapes using annular milling techniques necessary for atom probe analysis. The second lab houses the local electrode atom probe, which is a Kamika Leap 4000 XHR equipped with a reflectron lens. This is where we perform all of the atom probe tomography experiments. Atom probe tomography is a very useful technique. It uses mass spectrometry to identify the elements within your material, and it gives inherent 3D data sets with sub-nanometer resolution and approximately 10 parts per million sensitivity. The 3D data sets include a point cloud of atom positions that have an X, Y, Z, and mass to charge ratio. This data can be cut and binned in different ways, and localized compositions can be obtained. Some of the limitations of atom probe tomography include that there is a limited field of view and limited structural information. For those of you who are not familiar with atom probe tomography, it is quite a simple technique to understand. APT uses direct projection magnification, very similar to a projector in a movie theater. The main difference is that you're projecting from a 50 nanometer hemispherical surface onto about a 4 centimeter circular detector. This gives us about a 1,000,000x magnification. In this mode, we're just imaging the surface, but we utilize a pulsing mechanism in the form of a voltage or a laser pulse. This pulsing mechanism triggers a field evaporation event, and then we have a detection event. The difference in timing of these two events give us our time of flight that could then be changed into a mass to charge ratio. This is how we identify elements in our material. Elements that evaporate from the center of the needle end up hitting the center of the detector, and elements that evaporate from the edge of the needle end up hitting the edge of the detector. We then use this data from the detector and a computer algorithm in order to reconstruct our material in 3 dimensions. For each detection event, we obtain 4 pieces of information. These are the X position, Y position, time of flight, and sequence of detection. Because this is a destructive technique, and we know the volume of the needle before we field evaporate it in the atom probe, we can use the sequence of detection to give us the Z dimension when going from 2D detector space to 3D reconstruction space. After we field evaporate the specimen that we created in the focused ion beam and use the reconstruction algorithm, we then have the atom probe tomography data that we can analyze. This data consists of an X, Y, and Z position, as well as a mass to charge ratio. On the left-hand side, you can see the mass spectrum with several counts for each peak. Each count within this mass spectrum is labeled with an X, Y, and Z position. As you can see from the mass spectrum, we have titanium, aluminum, iron, and nickel within this sample. And we could individually select each of these regions of the mass spectrum and display their atom maps in order to visualize the differences in each of these elements. As you can see, we have the all ions, iron, aluminum, titanium, and nickel atom maps. We could see the titanium and nickel segregation within the L12 precipitates of this material. There are several different post-processing analysis tools that we can apply to the atom probe tomography data to better visualize the data or better quantify the elemental concentration profiles within the data. Some of these include 1D line profiles, 2D contour plots, radial distribution functions, frequency distribution analysis, and several other data analysis techniques. I'd like to show you how we could use the analysis tools in order to extract important information from the atom probe data using two examples from previous user projects. The first example is from Bert Vakhuizen's group from Utrecht University, in which we use APT to understand coking mechanisms at the nanoscale. On the left-hand side, you can see two ZSM-5 zeolites that were exposed to the methanol to hydrocarbons reaction for 1 and 90 minutes. You can see that after 90 minutes that the sample was severely coked. When we looked at this sample using APT, we found nanoscale regions that were very carbon rich and carbon poor. The carbon-rich regions can be seen by the high density of red dots. The red dots represent each individual location of carbon atoms. We can also use an isoconcentration surface, shown in red, that can separate the carbon-rich region from the carbon-poor region. We also further analyzed the carbon-rich region using entered atomic distances, and we were able to extract very, very small carbon clusters from the data set. When we performed a radial distribution function from the center of these carbon clusters, we found that the carbon clusters are agglomerating around single aluminum atoms. And this is not surprising because the aluminum atoms are the active catalyst sites at the atomic level. The second example I'd like to show you is from an aluminum copper alloy in which we can clearly visualize a theta prime precipitate within the atom probe tomography data set. As you can see, the field of view is very small, and we are only able to partially capture one of these theta prime precipitates. What we have here is an atom map where the aluminum atoms are blue and the copper atoms are orange, and we also have a 10 atomic percent copper isoconcentration surface that separates the theta prime precipitate from the matrix itself. Like I said before, we could clip and crop this data however we want. What we have done here is that we took a region of interest and sliced it for a cross-sectional view in order to do a compositional analysis. On the left side, you can see a schematic of the theta prime precipitate, and we could see that the viewing angle at which we're looking at the precipitate in the atom probe data. If we look at the bottom row, we have 2D contour plots of copper, zirconium, and manganese. We could see that the zirconium and manganese segregates to the interfaces, and that manganese segregates to different interfaces than the zirconium. What is also notable is that the zirconium levels that we are able to measure at the interface is at 0.4 atomic percent.
So my name is Bert Wekhuis, and I'm a professor of inorganic chemistry and catalysis at Utrecht University. It's a place in the Netherlands. It's one of the older universities on the European continent. And the university is a general university, so we have from law to medicine to also chemistry or catalysis. And my field is heterogeneous catalysis, and what I'm trying to do is to use spectroscopy, microscopy, analytical methods to understand better how solid catalysts function, work, deactivate, how they are made, how they operate, what their properties are.
Okay, thanks. Yeah, I know you have a very big group and that you branch out to a lot of different groups and you have a lot of collaborations. And I know that we've been working together through the CNMS for probably over 4 years now.
Yes.
And can you just help some of the user community to understand how the Atom Pro facility has helped you do your research?
Well, I'm already for years interested in knowing how, at a nanoscale, materials are structured, how they look like. And years ago, I have been at a conference, and it was in Santa Barbara on the campus where they have a beach. One of the universities who have a beach. And I was sitting with a colleague, and there I came across the method of atom probe tomography. And it took a while before I realized that it could be accessed. It could be that you could get access to this equipment. And then I have been working on zeolites and try to see if it could learn something. One of the challenges in the field of zeolite catalysis to know precisely where the atoms are, and more specifically where the aluminium atoms are in an aluminosilicate. And nano scale is an important, but even can you go even sub nanometer scale? And then later on, I have been working with you, and I must say that it was a pleasure. It was not always easy, but in the sense that it was easy to work together with you, but the topic itself is not always easy. And also materials wise, it's not always easy because you can have a material, but it can still fracture when you try to measure it with atom probe tomography. But looking back, if I now see what kind of progress we have made, it was certainly worthwhile the effort. And I'm very glad that we also have been making a mark in the field. I think we were one of the first who have been exploring for zeolite, or porous, microporous materials, how atom probe tomography can learn something on these materials. So I'm glad. I hope still we can continue to work together. And I also feel that the method has still a lot to offer.
Yeah, I agree. And I agree that it was challenging at first, particularly because it was such a new material system for the technique. And it's also just not a standard material for the technique. Typically, the historically atom probe has been used for very robust metallic materials that have very good structural features. And it's good to see that within the last 4 years since we started working together, there's a lot more groups that are starting to use atom probe on these types of materials, and they're kind of leading in our footsteps. So that kind of follows up to my next question is how did you end up hearing about the CNMS, and how did you go about submitting the user proposal for the first time? Because right now it's pretty much clockwork. We've worked together on several different proposals, but of course the first one was probably more difficult, and hearing about us is more difficult.
There are two things which I think are essential. First is there was an American scientist, actually, if I recall it well, it was Simon Baer, who first brought me in contact with Oak Ridge National Lab. And then it was a kind of cascade. I don't know exactly how it then went. We had a proposal, and we tried to get access to this facility. But also I have to say that, and maybe you remember it, that I also have been visiting you. So what I always find essential in cooperations is that you can see each other in each other's eyes. That sounds maybe a bit strange, but it is like, or that to sit around the table or to drink a coffee or whatever, it does not make everything what you cannot do now in Corona time. So that is really not good. I think that's one of the things what we miss, really miss, what I miss, I think many of us. But when I realized that the first time that people came from my group, postdoc, PhD, came to visit to your place, I also felt I should see the instrument. I should understand what it is. I should speak with the scientist behind that machine, if I may say that. So what is that all about? And I still recall I was at a conference. I made a trip where I made, it was from it was a material research conference. I forgot, what is it again? A very known city in your state, which is, sorry.
Nashville, maybe?
Nashville, that
Yeah.
was it. Nashville, I should know it right away. Nashville, so I landed in Atlanta and drove to Nashville. And from Nashville, I drove to Oak Ridge National Lab, and from there back to the airport. But it was because of a conference. I thought, it's not that far away. Just have a rental car, just go. And I must say, I still remember it when I met you and when we walked around on the campus or on the facility. You showed me around, and then you also feel that there is interaction. You also feel the other way around, I think, is that you feel that we as group are also interested, that it's not just, I would say, oh yeah, give me the data or give me the publication and that's it. No, it's together.
Yeah,
and I think that is something essential.
Yeah, and I feel that it's been a very fruitful collaboration, and I've also gotten along well with all your students and postdocs, and we've had very good communication, from all levels, from you to the students and postdocs and everybody that works with you. I'm just gonna have one final question. I was just wondering how this really, helps your students and postdocs coming to Oak Ridge to do research with us and to see the facilities that we have.
Well, first of all, I think that you only come or you only make the effort to travel overseas if there is top-notch facilities, if it has something to add. If it is what I would call mediocre, you will not do that. And the other way around, I think as well, is if we would come up with a mediocre proposal, mediocre materials, you would also not think you can benefit or that we can make something. So what does it bring? So what I noted there was it's top-notch facility, it's staff, technical, but also caring, if I may say call. I think it's not just like you have a pizza store and you say, okay, give me pizza, margarita, or whatever. And then, no, it is something like there is also, it's a package. And that package deal is top notch. It is technical or quality support, and then also a caring support. I think all the people which have been sent it around, I hear them sometimes they telling, and if I recall it well, you have been taking them out or at your patio or somewhere. There was a social activity. I've seen pictures of that, and I thought, okay, they care about it. So I also want to say that. Thank you.